Good evening, everyone. My name is Salman. I'm a computational physicist by background and at DSR to, like Antonio already introduced, to switch to data science and machine learning roles. And today I will be talking about my portfolio project that I built at DSR. The idea actually came about a bigger project that I wanted to work on for quite some time. And I would say like what you see today are some of the first steps that I took towards building this project that I had in mind for quite some time. So what was the problem that I was targeting? So think of a disaster happening in a city or like a defense problem. And think of the people who want to control this situation, like think of disaster management agencies, the military, etc. One of the problems they have is they have a huge stream of heterogeneous data streams from different sources, say a radar, LIDARs, whatever. That's what I try to depict here. Satellite images, you name it, right? So there are a lot of different sensor streams that are happening simultaneously. And it's often a challenge to kind of integrate this into one solution such that, or one platform, such that we can improve our strategies, make better decisions, or simply just be aware, situationally more aware of what's happening. So my vision initially when I started this was to create a live digital twin. By digital twin, I mean a simulation of what is happening on the ground by taking in all the sensor streams that are available and by doing this to aid disaster management and defense applications. And like I said, this has two main advantages. I mean, it's very clear that you get enhanced observability and monitoring of the situation. Additionally, the digital twin alone can be used as a simulation, standalone simulation. So you can look at a flood-prone city and simulate the most probable areas where a flood can occur and run simulations and test out your different strategies in a completely simulated environment, such that you can be better prepared to handle such cases. So, I mean, this is a very open-ended goal, right? It's a big project. You can't do this in 3 weeks, for example. So what I'm about to show are like some of the first steps that I took here. I plan to take this forward if possible. So these were some of the first steps. So what I did was, being here, I'm restricted in the amount of money I have to buy different sensors and drones, for example. So what I did is like I focused more on the digital twin aspect because I had a GPU. So I could do simulations on that and focus on the digital twin aspect of it. So I did this, worked on this CARLA simulation platform. So it's an open source simulation platform that lets you run different simulations, like you have a small city, think of like a video game, right? And it provides you a variety of different sensors that you can use. And it allows you to orchestrate different scenarios, mainly with ground vehicles. But like simulating disasters and conflicts and things like that, it's more complicated because you would need to render all these things in Unreal Engine or Unity or something and then import it. It's for future work. So I decided to stick with what CARLA provides. This is a simulation that I did. What you're seeing is like data created by me. It's like a city, a busy intersection in a city with like multiple cars moving. And my objective was to look at multi-sensor fusion, right? So one challenge is that you need to accurately detect objects that are moving around and you want to track them. And currently you can use RGB image feeds, like a camera feed to do this tracking. I wanted to see like how it can be improved with if we combine just images, not just images, but also LIDAR data, for example. What I did is like YOLO, you only look once. It's like a popular model in computer vision that lets you track objects on the fly. It works really well. So it's state-of-the-art, one of the state-of-the-art models. I tried to run YOLO on this, but as you can see, it doesn't work really well. The reason being that this model is trained only on common images, like not overhead drone stuff. So it hasn't seen anything like this. So it like kind of misdetects this as a train, for example. But what I did is like I found this data set. It's called VisDrone. It's not visible here, but it essentially has a lot of labeled images with different cars and a lot of different angles taken from drones. So I fine-tuned my version of YOLO on this data set. And what you see next is, this is like for nerds, we can discuss this later. It just shows that the training went quite successful. So loss or the error in predictions came down. Yeah, essentially, so this is how the performance looks like after fine-tuning. So it performs really good. As you can see, it can track almost all the vehicles. Even though the image is, the altitude of the drone is really high and the cars are really tiny, it can still see that. It's performing well, but okay, well, my goal was to enhance this, right? So I checked off what impact this has on the visibility. I created a simulation which is very foggy. And as you can see, it's struggling, right? So this can be improved if it has information about LIDAR data. So not just relying on pure visuals, but it looks at laser pulses that are reflected off of these vehicles. This is where I kind of hit a roadblock because it's not very easy to work with drone visuals from this angle. I will spend a few slides explaining why this is. I plan to do it in the future, but I did something else, which I will show after I explain why LiDAR can be complicated in such angles. So essentially what LiDAR does, it's commonly used in autonomous cars these days. It's very common in most modern cars. Teslas, for example, Tesla doesn't use LiDAR. The other car manufacturers do. So it essentially shines a laser light along this thingy, which creates a, it's restricted, the laser light has like this limited FOV that restricts it to this cylindrical region. For example, this works for cars, right? Because the cars don't expect anything to fly up to it from above, at least in normal circumstances, and objects are moving along this plane. So it can detect all of that, and it can also fuse it with RGB images, right? So it sees these things the same way as the LiDAR would see it. But in my case, I mean, this is a hacky image, but what it shows is that if I point a LiDAR directly downwards, it's essentially scanning like this plane. What this means is that so this is my LiDAR returns for this drone pointing at exactly this image. As you can see, it's only getting one slice because it's just doing this in one axis. And additionally, like, I mean, even if I get this, it's like poor resolution, and fusing can be a challenge, right? So I was already like kind of past my 3-week session at this point. So I had to refocus. I tried to look at other modalities, like not LiDAR. Thermal would have been really easy if I had a thermal camera, but unfortunately, it's very hard to simulate because you have all these heat signatures of a lot of different elements in a city. So most simulators don't support it out of the box. The other sensors, again, these are like this point of view is like really hard to work with since like the altitude is very high. The resolution is really bad to really work with. There are techniques to overcome this, but I figured that it's probably not possible to do it within the time frame. So what I did is I focused to show something for the demo, which was to combine natural language with object tracking. So essentially, I did combine a vision language model, which is like a LLM, a large language model, but it can also detect things on the text. You describe what the object you want to track is, and it understands what it looks like, and it performs on the fly on video. So if I ask it to track a hostile vehicle, for example, and give it a description of what it looks like, it can work with real-time video and kind of track it. So I will show us. So right now here I can enter a query or a description. Essentially, it's kind of lagging, I think. Yeah, so right now I don't have any query selected, so it's tracking all the vehicles, right? So here you see the raw footage, and here is the annotated video. So now maybe I can ask it to track red cars. Apply query. Okay, it takes a bit of time because the VLM is going through it. And yeah, as you can see, it's only tracking the red car. And each time a new red car comes in, it's going to know. So how am I doing this? So essentially what I do is I look at the bounding boxes provided by YOLO, and I ask my VLM to test if this car matches the description. And this is something that modern vision language models can do. Even if you just give it a text, it's been trained on so many images that it knows what a red car looks like, which is quite cool. So it can have a lot of applications like this if you combine it in the right way. So you can see tracks it, sees another red car, tracks it. So yeah. This is a short demo that I prepared. Keeps a unique ID of all the embeddings, and this Qwen 2.5 is the vision language model that I used to combine my text queries with an image. All right, this kind of brings me to the end of my presentation. Thank you very much for your attention. And I would also like to thank my mentor, Christoph, and all the DSR teachers, Antonio especially, because he was the computer vision guy and main inspiration behind all this, and also Jose and all the other project mentors, and of course, Arun and Ebin. They've always been very helpful, and all my batchmates. Thank you so much.